everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Today we're going to be looking at integration by parts and using it to bring up into being areas under curves, which will connect with more traditional approaches to calculus. So integration by parts is an important technical device that has independent interest because it helps us actually calculate integrals. So the starting point is really the product rule going back to Faulhaber's algebraic derivative d. If you have two polynumbers p and q, then the derivative of p times q is p times the derivative of q plus q times the derivative of p. That's the product rule that we're all familiar with. The other ingredient that we need is the derivative integral composition theorem, which tells us what happens when we combine a Faulhaber derivative with a Faulhaber integral. So the first one is if you do the integration first and follow it by the derivative, then you get back to where you started. So I represents the identity operator. On the other hand, if you differentiate first and then integrate, you almost get back the original polynumber, but not quite, because you have to subtract the constant part of the polynumber. And the reason for that is that when we differentiate, a constant function, say a non-zero constant function, is sent to zero. And then when we integrate it, we cannot get that constant back again. So we lose the constant part when we differentiate and then integrate. So now we're going to put these two things together to get the algebraic integration by parts formula, which is right here. Okay, so what we're going to do is we're going to apply the S operator to both sides of the product rule. So let's look at the right-hand side. So if we integrate p dq plus q dp, well, the integration operator is linear, so this is the integral of this plus the integral of this. And that's going to be then the integral of this. Now that's covered by this case here. So we're going to get d composed with s, so we're basically getting this thing minus a constant term. Now to get rid of that constant term, which is a little bit of an inconvenience, we look at a relative integral. So we're going to integrate from t to u. I'll remind you what that means. That s sub t to u of, say, p is the integral at u minus the integral at t. So it's a difference between two integrals, one at the top one and one at the bottom one. Okay. So when we take the difference of two integrals, then that constant term ambiguity is washed out and it disappears. So the net effect is that when we apply the Faulhaber integration S operator to this equation, we get S from t to u of p dq plus S from t to u of q dp will be equal to the difference between the identity here at u and at t. So that pq from t to u. This means take pq and evaluate it at u and subtract the value at t. So that's the algebraic integration by parts formula, which is really a pretty well a direct consequence of the product rule combined with this derivative integral composition theorem. So as an illustration, let's look at an interesting family of integrals. We're integrating x to the k times 1 minus x to the l from 0 to 1. So k and l are natural numbers here. And that's going to be some number, which depends on k and l. Let's call it c sub k comma l. Now, we can use integration by parts because this is a product here. So let's think of p as being, say, x to the k, and q equals 1 minus x to the l. Then the integration by parts formula tells us what? That the integral from 0 to 1 of p times dq, so p is x to the k, and what is the derivative of q? Well, the l comes down. We also get 1 minus x to the l minus 1. And then we have to multiply by the derivative of what's inside. That's the chain rule, which is a minus 1. So there's a minus 1 appearing, and then there will be a 1 minus x to the l minus 1. The next term is the integral from 0 to 1 of q dp. So we're taking the derivative of the p term, which is k times x to the k minus 1 times the q. And altogether that's equal to the product of these two things, p times q, which is x to the k times 1 minus x to the l, evaluated from 0 to 1. Now, if k and l are both strictly positive, like 1, 2, 3, etc., then there will be an x term, there will be a 1 minus x term, and when we evaluate this thing from 0 to 1, both endpoints will give us a value of 0, because this term's 0 when we substitute 1, and this term's 0 when we substitute 0. So the right-hand side is going to be 0. And we just get a relationship between these two things, which we can write this way. So we can take the k here and pull it out front because it's linear. And then what we see inside here is c sub k minus 1 comma l. And we can take this thing to the other side because there's a minus sign here. So we can take it to the other side, bring the l out front, and then what's left inside is c sub k l minus 1. So this little formula here tells us that we can relate what happens when we drop the k index by 1 with what happens when we drop the l index by 1. Those are these sort of factors, k and l. Now, in addition, it's relatively easy to see that c sub 0m or c sub m0 is 1 over m plus 1. That's an easy exercise I'll leave to you. And so then the possibility emerges that we can then calculate what c sub k l is for a general k and l by repeatedly using this sort of recursive formula to bring things down to one of these two cases. And so we can at least aspire to getting actual formulas for c sub kl, and I'll leave that to you as an exercise, and we'll talk about it in the actual online course. And now let's bring the integration by parts together with the fundamental theorem. Here's the fundamental theorem, which tells us the signed area from t to u of the curve p comma q, these are two polynumbers, is given by this expression involving just Faulhaber derivatives and integrals. It's 1/2 the Faulhaber integral from t to u of p dq minus q dp. Notice there's a minus sign there. So here is our integration by parts formula, just rewritten a little bit so everything's on one side. 0 equals pq from t to u minus s from t to u of p dq minus s from t to u of q dp. Now what we're going to do is we're going to add and subtract 1/2 of this formula to this formula. So let's see what happens when we add half of this to this. Well, the left-hand side is still s from t to u of pq. And when we take half of this, well, we'll get a half of pq from t to u term. Now half of this added to this will get rid of that term because there's already a half in front of the p dq. So there will be no more term like this. On the other hand, when we take this minus q dp term and add half of this one, they're equal. So we're going to get just a single s from t to u of q dp. The two halves combine to give us a coefficient of 1 there. Okay? So the effect of adding half of this to this is to get rid of the p dq term and sort of elevate the q dp term so that now it has coefficient 1. And the price we pay is that we now introduce this pq from t to u term with a half in front. Similarly, if we take this and we subtract half of this. So we subtract half of this. Well, in this case, the q dp term, we subtract half of this, there'll be a minus sign with another minus sign, that's a plus sign. So that'll cancel with this one here. So those terms will disappear. And it's these terms that will add. So we're going to get this term plus essentially half of it for a total of s from t to u of p dq. But we also have to subtract half of this, so minus 1/2 of pq from t to u. So we get two alternate forms for the fundamental theorem. These are alternate formulas that allow us to calculate the signed integral of a curve involving Faulhaber integrals and derivatives. But both of them only have sort of one term. There's not two terms inside. We'll call these formulas 1 and 2, and we might say they're the first and second asymmetric forms of the fundamental theorem. So these are important alternate formulas that capture the same kind of information as the fundamental theorem, but in some situations they are easier to apply. Now it turns out that both of those alternate formulas have geometrical interpretations, and they tell us something about the geometry associated to a curve. Let's illustrate that with an example. Simple example of a parabola, y equals x squared. We're given by the curve alpha, alpha squared. There it is. But we're only going to be considering the portion of the curve from 1 to 2. Okay, so when we have 1, we're at the point 1, 1. We have 2, we have the point 2, 4. So it's that portion of the curve that we're interested in. And how do we get the signed area of that? Well, according to the fundamental theorem, that's 1/2 integral from 1 to 2 of p dq. So alpha times derivative of alpha squared minus q dp. Alpha squared times the derivative of alpha. Okay, well, the derivative of alpha squared is 2 alpha. The derivative of alpha is just 1. So we get this expression here. And inside here we get 2 alpha squared minus alpha squared. That's just alpha squared. And when we integrate that, we get alpha cubed over 3. So we have 1/2 alpha cubed over 3 evaluated from 1 to 2. Okay, so the 3 can come out front. There's a factor of 1/6 there. And then we have 2 cubed minus 1 cubed for a total of 7/6. So that's the signed area determined by this portion of the curve. And it geometrically represents the area formed by the curve and these two lines emanating from the origin. So that slice there that's in red. Now let's have a look at the alternate formula 1, okay, which is that the same signed area is 1/2 of p times q from 1 to 2 minus s1 to 2 of q dp. Q is alpha squared, p or dp is d of alpha. Okay, what does this amount to? Well, here there's an alpha cubed inside here, so we have to evaluate this alpha cubed at 2. We have to subtract the evaluation at 1. That's that difference there. And here we're integrating from 1 to 2. This just ends up being alpha squared. Okay, so this can be expressed as 1/2 of 2 cubed minus 1 cubed, and this is minus, again, the integral of alpha squared is alpha cubed over 3 from 1 to 2. So we get this expression, minus 1/3, 2 cubed minus 1 cubed. Common factor of 2 cubed minus 1 cubed, 1/2 minus 1/3 is a 6, so we get 7/6 as before. So yes, the formula does work. But let's have a look at what it means geometrically. So what are the geometrical meanings, say, of the quantities appearing here in this formula? Let's look at the second line. So the 1/2 of alpha cubed at 2. This is the x-coordinate times the y-coordinate at the point 2, so associated to that point there. So we're talking about this times this over 2. This term right here corresponds to the signed area of this big triangle. And this one here is the same kind of thing. It's an x times a y associated to this point here. So it's the signed area of that small triangle. And then, so what are we saying? So that the signed area in red, okay, is equal to the signed area of the big triangle minus the signed area of this little triangle minus something else. Okay, but geometrically we can see what that something else has to be, because look at the big triangle, look at the signed area of the curve in red. There's the little triangle. If we take the big triangle, we subtract the area of the curve and subtract the small triangle. What we're left over is the area under the curve. or between the curve and the x-axis. So this region here is exactly the thing that's expressed by this quantity. In other words, it's the integral from 1 to 2 of, well, we're talking about the first formula, it's q dp. So this kind of analysis, which really goes back to Leibniz. Leibniz was very fond of this kind of analysis using triangles, comparing areas under curves with areas subtended by the origin. So this is exactly along the lines of what Leibniz would have been thinking. This shows us that this term that's appearing here in this first alternate form really is capturing the idea of the area under a curve or between the curve and the x-axis. And that's a very fundamental, important observation. So now we're going to officially introduce signed x areas for polynomially parameterized curves. We'll say that the signed x area of the curve segment gamma from t to u, where gamma is a polynomially parameterized curve given by p comma q. This signed x area is expressed this way, and this is what it's equal to. So we write Sx from t to u. So it's like a signed area, S, but Sx, meaning that it's a signed x area. Okay, still going from t to u and still of the curve gamma. And the definition is it's going to be the Faulhaber integral from t to u of just q dp. Exactly that expression that we saw in the previous example corresponded geometrically to what geometrically we see as the area under the curve. So geometrically, this is the signed area of the region A, AX, BX, B. Have a look. Here's a curve, gamma. There's A, gamma of t. There's B, gamma of u. There's the origin. The signed area of the curve would be, represented by arcs going from the origin to the two endpoints, looking at that wedge. Now we're doing something different. Now we're looking underneath the curve. So we take the point A and we go straight down to the x-axis, and we'll call that point A sub x. And going straight down to the x-axis from B gives us the point B sub x. And what we're capturing here is the area formed by this kind of curvilinear rectangle. It's got rectangular sides, 3 of them, and then there's this fourth side, which is like a curvilinear or curve segment. So it's not really a rectangle. And I put the region A, AX, BX, B in quotes, because it's just a geometrical interpretation of what's going on. It's bounded by the spline A, AX, AX, BX, BX, B, and then the actual curve now from B to A. Notice that we're assigning a positive orientation here. We're going counterclockwise. That's the positive orientation. And so if the curve is going from here to here, we'll get a positive number in a situation like this. So Sx from t to u of gamma, that is now the area underneath the curve. That's a definition of it, and that's how we're going to evaluate it. Okay, so let's have a look at an example. So if we start with the function y equals x to the n, which we prefer to think of as the curve, alpha to the n, then the signed x area from t to u of gamma is, by definition, the Faulhaber integral from t to u of q dp. Q is alpha to the n, and dp is the derivative of alpha, which is just 1. So we're integrating alpha to the n. When we integrate that, we get alpha to the n plus 1 divided by n plus 1. So there's an n plus 1 in the denominator. And then we evaluate from t to u. So u to the n plus 1 minus t to the n plus 1. So we are recovering the standard formula from calculus, which is the area under y equals x to the n from t to u. Here's another example which is less familiar from classical calculus because we're talking about a curve which does a little bit some more wandering around. So this is we might call the alpha curve. It's a spread polynumber curve given by the two spread polynomials S2 of alpha and S3 of alpha. So these are polynomials coming from rational trigonometry. They're actually playing a very important role, but we don't need to worry about the details. They just happen to have the values 4 alpha times 1 minus alpha, that's S2, and S3 is alpha times 3 minus 4 alpha, all squared. If we graph that as a curve, we get, at least from t equals 0 to say u equals 1, we get a loop like this, which is like alpha. Okay, so suppose we're interested in the signed x area of this curve from 0 to 1. What's the signed x area of that looped curve? So that's more challenging. So classical calculus gets nervous with examples like that because we're doubling back. It's no longer a function, it's no longer a single valued function, it's actually a curve. But no problem, it's polynomially parameterized, so all our theory applies. What do we have to do? We have to take the integral from 0 to 1 of q dp. There's q. And the derivative of this is 4 minus 8 alpha. Okay, so this is a polynomial. You have to work out what that polynomial is and integrate it from 0 to 1, and you get 2/5. What does it mean geometrically? Well, if you think about it, it sort of represents the portion that's in green here, represented positively, and the portion in red here, but that's sort of contributing negatively. So it's actually kind of a difference of what we might say is the signed area of that piece and that piece. And these other pieces either make no contribution or the total contribution cancels out. So I'll let you think about the geometrical meaning of that answer of 2/5. Now I want to go back to the second alternate form. There were two alternate forms of the fundamental theorem. The second one is also important. So let's go back to our example of y equals x squared. I remind you that we calculated the signed area from 1 to 2, that portion of the curve, and we got 7/6. Now there was also a second formula, and I remind you what that is that the signed area from t to u of pq is the integral from t to u of p dq minus 1/2 product pq evaluated from t to u. So if we apply this second formula to this situation, we get that the signed area is s from 1 to 2 of p is alpha, and then we have d of q, so d of alpha squared, and minus 1/2 the product alpha times alpha squared from 1 to 2. Okay, here we're integrating 2 alpha squared, and here we're taking the difference between 1/2 of alpha cubed at 2 and alpha cubed at 1. So we get the integral 2/3 alpha cubed from 1 to 2 minus 1/2 of 2 cubed minus 1 cubed. This is 2/3 of 2 cubed minus 1 cubed minus 1/2 of 2 cubed minus 1 cubed, and that gives us 7/6. Okay, so same kind of thing that we did with the x one. But now we want to have a look at this intermediate line and interpret what's going on here. Okay, so we're still evaluating this red area subtended from the origin, but now we're expressing it in the following form. So what are the ingredients here? Well, there's 1/2 alpha cubed of 2. Well, this really represents the product of the x and y at the point 2. So this is really like the negation of that signed area of that big triangle there. And here is, again, another triangular area corresponding to the parameter 1 that corresponds to this point here. That's this triangle here. Okay. So what we're saying is that the red area, which is on the left-hand side, is equal to this quantity, which we're trying to interpret, minus the area of this big triangle plus the area of this triangle. So if you stare at that for a little while and ask yourself, okay, what does it mean? What does this necessarily then geometrically represent? You'll see that it represents the area formed from the curve from 1 to 2 under it in the direction of the y-axis. So I'll paint it like this. Okay? So consider this equation. So we've got this area to the left, in this case, of the curve, all the way over there. And now we subtract the area of this triangle, so that removes all of that. But then we have to add back the area of this triangle, okay, which will then cancel that thing that was sort of subtracted before, and contribute again the portion there. So that's exactly the interpretation that we need of this quantity S12 of the PDQ. It's representing, in this case, the area under the curve towards the y-axis. Not really under, maybe to the left of, okay, or between the curve and the y-axis. So that's playing a symmetrical role to what we saw the other term was in terms of the area between the curve and the x-axis. So these two different areas between the curve and the two axes can be thought of quite in a symmetrical way. And so now we introduce signed y areas for polynomially parameterized curves. The signed y area of the curve segment gamma from T to U, where gamma is PQ, is, here it is, Sy from T to U of gamma, and it's by definition the Faulhaber integral from T to U of PdQ. The x1 was QdP, this one is the y1, it's PdQ. And geometrically, this is the signed area of the region. Now A, B, B sub y, A sub y, bounded by the curve gamma from A to B, and then the segment B to BY, BY to AY, and AY to A. Maybe we should put a spline thing over that. These are actual splines. Okay, so it's entirely analogous. It's just we're integrating PdQ instead of QdP. We want the area under a curve, between the curve and the x-axis. We integrate QdP. We want the area between the curve and the y-axis. We integrate PdQ. The situations are completely symmetrical. And the original defining signed area in terms of the portion subtended by the origin is some kind of combination of these two things. So actually sort of a difference. It's more symmetrically poised between the x and the y axes and doesn't actually depend on the axes themselves, just on the position of the origin. So just to wrap up with two examples. So if we go back to y equals x to the n, our standard function, then gamma is also represented by alpha to the n. And then the signed y area, Sy from T to U of gamma, is the integral from T to U of P dq. There's the P. The dq will be n times alpha to the n minus 1. And we get n over n plus 1 times u to the n plus 1 minus t to the n plus 1. And a slightly more sophisticated spread polynumber curve is the Trefoil curve with entries S4 of alpha and S3 of alpha. This is what S4 of alpha happens to look like. There's S3 of alpha that we've already seen. And here is a picture of the Trefoil curve, kind of bounces around inside the unit box there. From t equals 0 here, all the way up to u equals 1. We might be interested in what's the signed y area of this thing from 0 to 1. Well, we take the Faulhaber integral from 0 to 1 of p times dq. So we have to take the derivative of this, which turns out to be this, and then you have to evaluate all of that, just polynomial expansion, and then integrate, and you get 8 over 7. You can check. So we are now in a position of connecting with standard calculus, but we're seeing it in a more general picture because we can deal with curves like this. And then there'll be cancellation, because some of the areas are kind of positively oriented and some of them are negative, and there'll be suitable cancellation. but still that's all part of the story. It's all algebraic. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.